All right, so I kind of like tentatively looked at some of the grades for the last exam, so they look pretty good. Obviously, they're all missing 25 points, so they won't look good as of right now. But I should be able to. I think I'll probably start grading the exam first, and then kind of go back and grade that third Excel assignment that was due at the end of the week last week. So throughout the week, I should have those all done by the end of the week at some point, and you'll kind of know what your exam score was. I'll make some changes on Canvas so that you can see kind of what your best exam score is, and then what your next best is, and kind of weight those accordingly, because for everyone it could be a little bit different, right? So I'll start getting those kind of updated as I get those exam 2 grades done. So Canvas will look a little bit different, but I'll explain what the new columns and things in Canvas mean in terms of kind of calculating your grade once we get to that. So probably Wednesday, I'll have those exam scores and then kind of your highest and lowest, and kind of explain that a little bit more. But until they're up there, it's a little bit hard to, probably not worth our time to kind of have that discussion until I have those changes with the exams fully graded. Okay. Any other questions for me?
On Canvas, it said the exam was out of 103.75.
Yeah, so kind of like the last one, I'll get that changed once they're fully graded, because it's only going to be out of 100 points. So kind of like the last one, you could have technically got 104, but it wasn't out of 104, it was out of 100. But the way I have to have it initially set up so I can get you the question, it'll appear until they're fully graded as though it's out of 103 point, but it's only out of 100. Yeah. Yep. Any other questions before we kind of jumping into some new stuff here today? Okay. Make sure there's nobody on here. All right. So I put up kind of this week's lecture slides, as well as some Excel files that we might jump into a little bit today, but for sure by Wednesday if we don't get there today. So what we were doing last time, and whether or not we knew the sample variance or the variances or the population variances, we were looking at the difference in 2 groups' means, right? So this could have been something like, do male physicians and female physicians have a different salary, or is one greater than the other, is one less than the other, right? Those are some interesting questions. Another similar thing we can do is called matched pair sampling. So this is going to be kind of the first way in which we're trying to understand whether or not a characteristic influences maybe a particular variable that we're looking at. So does gender, for example, kind of impact kind of whether or not salaries are different? Right? That was kind of what we're doing with 2 population stuff, but matched pairs is going to be able to do that a little bit better. So instead of having 2 populations, we're just going to have 1 population in which we have like either two variables collected, or quite often it's the same variable but in 2 different time periods. So maybe I think the example I have kind of set up just to give us a motivating example here is, maybe I'm wondering if I rearrange the workstation, if productivity increases after that kind of rearrangement. So I have the same 10 workers. I have this variable of, I can see what their before productivity was, and then I can see what their after productivity was. I then want to think about, okay, has productivity increased, decreased, or changed, right? Those are 3 kind of possible things I can be thinking about. So I'm going to call this difference variable, right? The difference between each worker's before and after productivity. So I have 1 and 2 here because it doesn't always have to be before and after. It could actually be something like, within the same, I'm thinking about a good example here. So I think the one I give you in Excel is within the same counties, right? Do I see a difference between kind of male and female suicides, right? That's the one data set we'll look at in Excel. So it doesn't have to necessarily be before and after time periods, but that's probably one of the most common kind of applications of this matched pairs. So once we have this difference variable, right, we can find the average difference, and then we can also find what the variance is in this difference. Right? So what this is going to look like is something like, so let's say, I'll use a mark that shows up a little better. So maybe I have like all these worker ID numbers, so workers 1 through, 1 through 10. And then going to have what their before productivity was and what their after productivity was. I don't know. These don't necessarily have to make a lot of sense at this point in time in terms of how we're measuring productivity. Is it in units, or is it in the number of claims processed or something? But what we're going to do is we're going to create this difference variable, which is just for each worker, right? It's the same one sample, but we're going to look at the difference between before and after. So their after productivity minus their before productivity. So here this would be 2, 1. For this worker, it was negative. Their productivity actually decreased. Once we have done this for every single worker, we now essentially just have this variable x, which is the difference in productivity. Well, we can find the average of x, and we can find the variance of x. We're going to do it by hand. We could use Excel to do this. It's essentially we've gone back, right? Once we've calculated this difference variable, well, now if we want to do hypothesis testing or confidence intervals with this difference variable, it goes back to just a one population example where all I really have is a sample mean. It's notated a little bit different here because it's not like it's not the mean of one variable, it's the mean of this difference variable that we created. And then I would also have kind of a sample variance, which is supposed to be a 2. Right? I have the sample variance of this difference variable. So it goes back to one population where I've got a sample mean, but only a sample variance. And then everything's really exactly the same as we were doing before. We only have a sample variance, so we're going to be using the student t-distribution. We can start to set up hypothesis tests and confidence intervals for this statistic. So that's kind of what we're doing, what's going on behind the scenes, and I'll show you an example in Excel today as well that'll, I think, hopefully make it a little more sense. But if that's all we're doing, right, it's really the confidence interval will be the same thing we did for a sample mean with a sample variance. It's just now the notation is a little different because we're not using one variable. We're using this new difference variable that found the difference between kind of two pre-existing kind of variables, right? Before and after productivity, okay? But really, once we plug the numbers, it's going to look virtually the same as what we were doing before with confidence intervals, okay? So we'll still look up that student t-value that gives us alpha over 2 on either side of our interval. Our degrees of freedom goes back to being simple, where it's just n minus 1, because we only have one population now, right? We're collecting before and after on the same kind of whatever, in my example, 10 workers, right? Or I could do something like, has the amount of information, my stat students knows gone up or gone down or anything different? Well, I could have kind of before and after kind of knowledge, take the difference, find the average kind of change in that knowledge, and kind of build this confidence interval. Hopefully all the values would be above 0, right? Where I have a positive change in kind of how much they know. So it's really not a lot different than what we did before, right? So we think about kind of this example where we have productivity. Let's say I go through those 10 workers, I find that difference variable, and then I look at the average difference, 8.5, and I have the variance on that difference, right? Well, what this is really telling me is the sample evidence I found was that the average worker, their productivity actually went up, right? The average change in productivity was 8.5. So this difference variable is kind of like a change variable, right? What was the change in productivity before and after, right? So if I wanted to build this 95% confidence interval, right? Well, I've got the average difference. I got my sample variance for that difference. Sample size was 10 workers. It's really just a matter of finding that student t-value, right? So if I want the 95% confidence interval, what I'm thinking about there is my alpha is what? 0.05. Okay. So I found a sample difference of 8.5. I'm going to build my confidence interval around that such that alpha is outside of the interval, or half of alpha is on each side. So I want 0.025 in kind of each side of my interval, or each tail. My degrees of freedom is just n minus 1, so what, 10 minus 1 here, or 9? It's just using that student t-tail again. So we go back. Must have closed it out. So let's go student t-table, right? We wanted 0.025 in our tail, degrees of freedom 9. So 2.262 will be that student t-value we need. Now we have everything that we need to kind of, we have something to plug in for every component of our upper and lower bound equation now, okay? So we got that t-value, plug that in. We plugged in our sample difference, our variance on that difference, our sample size. So here's our confidence interval. So I've got what? 0.6 and 16.3 for my upper and lower bound. So visually, right, 0.6 is my lower bound, 16.3 is my upper bound. Here, if I'm kind of the manager, I look at this and say, well, with 95% confidence, I can say this kind of workstation layout change has increased productivity, right? The only possible value that the true kind of difference in before and after productivity, well, the only possible values with 95% confidence I could say that it is somewhere between 0.6 and 16.3, which are all positive. So with 95% confidence, I can say this workstation layout change actually increased productivity. Okay? So same kind of idea as before, right? These confidence intervals are most interesting when they don't cross over 0. Because let's say this was, I don't know, -3. Well, one of the possible changes in productivity could be 0, right? If that was the case. So it's a lot more interesting when they're all kind of positive values in my confidence interval or all negative. Any questions on that? Okay, so this is really kind of goes back to one population stuff, almost like a little bit easier. So really on this final, I think I had a question maybe before class completely started, but which was, will it be comprehensive? So it's going to be all new stuff on the final. This will kind of be like the low-hanging fruit, hopefully. Like we've done a lot of this. This looks kind of like old one sample stuff. Shouldn't be too bad. Okay. So if we can do confidence intervals, you can imagine we can probably also do some hypothesis tests. Right? Now here it's the exact same thing we were doing before. It's just instead of the true population mean, we're thinking about the true population mean difference, right? Because it's kind of just notating that, yeah, this isn't one variable. We kind of created this variable by taking the difference of two other ones. We still have greater than sign of the alternative, so greater than our right tail test, less than the alternative hypothesis, so less than our left tail test, and a not equal to sign, which is a not equal to or two tail test. So our test statistic is going to look very similar to what we're doing with sample means. It's just now we have this sample difference. Right? But once we have that difference variable, it's just a variable. We treat it exactly the same way. Now here, quite often in those two population examples, I was thinking about always having that assumed true difference be 0, and that still will kind of apply here, right? In this workstation one, you can imagine some of the tests I might want to do are, well, did it increase productivity? So is that difference greater than 0? Did it decrease productivity? Is that difference less than 0? Is productivity any different at all, right? So is it anything other than 0? But I could also do things like, did it increase productivity by, I don't know, more than 5 units? So then I could assume that true difference is 5, the true difference is 5 units, and then try to test for whether or not it's in fact greater than 5 units or less than 5, whatever kind of my hypothesis test I want there is. Now, like I said, more often than not, we will kind of keep this at 0. I think the examples we'll go through today are 0. I'll show you what it looks like in Excel if you want to use anything other than that, right? Anything other than the assumed true difference of 0. So for this example, we've got our test statistic equation now. We've got all the information we needed. If we do use that 0, right? So did productivity just change at all? Right? Is it anything other than 0? So we'll assume that instead it's equal to 0 for the null hypothesis. We would have that average difference minus the assumed true difference of 0, plug in our variance and our sample size, and we get our test statistic, right? Doesn't look a whole lot different than what we were doing before. Okay? In fact, you can kind of imagine if I kind of write these out right next to each other, just to really hammer home this idea because we're going to kind of extend it even more. What were we doing before? We had now we've got the difference minus the assumed true difference. Right? Looks very similar. Right? Because remember, when we're calculating these test statistics, we're always subtracting the assumed true population value of the statistic we're interested in. So for a sample mean, we assume the assumed true population mean. For sample difference, we subtract the assumed true population difference. And then we always divide by the standard deviation of the statistic we're interested in. So divide by the standard deviation of our sample means. Divide by the standard deviation of our sample difference. Right? So it's the same format, just a little bit different notation now. Okay? Any questions on that? Shouldn't be too bad. All right, so, we could go through another example, really similar, but now maybe we're looking at before and after kind of calories consumed after Starbucks starts putting up what the actual calories are in their drinks, right? So maybe you want to test for whether or not liquid calorie consumption has decreased, right? So what you want to test for is my alternative hypothesis. If I want to know whether or not it's decreased, when I think about my difference that I'm looking there, a decrease in calories consumed would give me a what? Positive, negative difference? Which one? If I think about after minus before, if they've decreased, then this difference would be what? Yeah, less than 0, right? So that's going to be my alternative hypothesis is that true difference, right? Is that true mean difference less than 0? I'll assume the exact opposite is true for my null, which would just be, is it greater than or equal to 0? So here, my alternative hypothesis is this true population difference less than 0, have calories decreased. I'll assume the opposite is true, stack the deck against myself, okay? So I've got what type of tailed test here? Less than sign in the alternative hypothesis, so left tail, right? So if I'm thinking about, well, I guess not my test statistic yet. I almost jumped the gun. So let's say we go out, we get 40 different Starbucks card holders, and we find that their average difference is 2.1, and we have a variance of 64, right? So we've got our variance, our kind of average difference, our sample difference, our sample size, and we have the assumed true difference that comes from our null and alternative hypothesis of 0. Which kind of makes this easy. What we're thinking of here is, what's the distribution of my sample differences? Well, they should be normally distributed around whatever that assumed true difference is. So the assumed true difference, I guess, what would we call this? We would call U0 of this difference, right? We assumed it was 0. We found a sample difference of 2.1. So right away, I know my test statistic is going to be what? If I'm trying to, this is a normal distribution. I'm trying to turn it into something that I can use one of my tables from, either standard, normal, or student t. Well, we already said this is going to be, we only ever have a sample variance, so student t distribution. But if I see something that's above the assumed true difference, then my test statistic should be positive, right? And it makes it a little bit easier when that assumed true difference is 0, and then if I see something above it, I know for sure it's going to be positive. If I see something below it, I know it would be a negative test statistic. So right away, I know I have a positive test statistic, and from here, it's a matter of plugging these into that new test statistic equation we have. All right, so it was what? Take the sample difference you're interested in, subtract the assumed true difference, divide by the standard deviation of that difference, which is just the square root of, what was it, 121 was the sample difference we found, I think. And I had 40 Starbucks card holders. So it's just a matter of getting that plugged into our calculator at that point. I'm guessing if we look at this, it's probably going to be 1.66, all right, if we get that entered in. Why could I probably guess that's the case? Well, a test statistic of, right, we already said it has to be positive, so I can rule A and C out right away. Probably think it's not going to be as high as 10, because that would mean the sample evidence I found was 10 standard deviations above the assumed true value of 0. We weren't that far away from 0. Our variance isn't like super small here. So if I had to guess here, I'm guessing if we compute this, we'd probably get D. And sure enough, if we plug those values in, that's what we get. Right? And I have a 2.1 here. I guess technically we could write in 2.1 minus 0. But right, subtracting 0 doesn't change anything. And I don't know why I said it was 120. It was only 64. Sorry. It was only, the variance that we were given was only 64. So if you were kind of following along there, this was 64, right? I was thinking of a different example, I think. Okay. So that should be pretty straightforward. Now, we think about our rejection decision here. What type of tailed test did I have? Kind of this left tailed test? What did I actually kind of find? Yeah, right, that it increased. So right away, if my null hypothesis is that it's greater than or equal to 0, what do I know my rejection decision is going to be? I found evidence that supports the null. So am I going to reject the null? No. I don't have to go through, do anything else. Now I could do the whole critical value approach or p-value approach. And once I get to the end of those, I'm both, I'm going to find a p-value that's really, really large, a test statistic that doesn't quite kind of make it into the, past my critical values, specifically because my critical values will be what sign? If I have a left-tailed test, yeah, negative. So my critical values, they'll be coming from that student t distribution. They're going to be the critical values that give me kind of alpha in this lower left tail. No matter what level I want to test at, they're going to be negative. So when I go look at my rejection kind of regions, that test statistic, I know it's going to be positive. So it's not even going to be close to that rejection region, right? If I think about my p-value, it's kind of a weird one here. Because for a left-tailed test, the p-value would be the probability I saw something that was far away from the nulls I did that went against it, or anything to the left for a left-tailed test. So my p-value is going to be huge. So if I only reject my p-value is less than alpha, I'm going to have a p-value that's greater than 0.5 here. It's not going to be less than any of my alphas. Right? So I can go ahead and go through those steps, but if I just remember that what I'm doing with this hypothesis test is if I find evidence that goes against the null, I'm trying to figure out, does it go against it enough to where I can say with different levels of confidence that I can reject it? If I find evidence that supports the null, well, yeah, I'm not going to reject it. Right? I found evidence that supports it, so I would fail to reject it. Right? So that's kind of a unique example with that one where, if we think about our rejection, I left this slide blank with this discussion of if we found something that supports it, then for sure we're not going to reject. We could do kind of a confidence interval here. I just kind of put this one up. I'm not going to walk through this, but if you want an additional kind of confidence interval example, you could build one for this, nutritionist as well. Should be centered around that 2.1. It's really just a matter of kind of plugging those values in, finding your t-value that you need. Just give you another example if you want to work through on your own time. Okay, and then also allows me to kind of give you this meme that's a throwback to Napoleon Dynamite, which is another great movie you should all watch. So. All right, so this should give us two, and I kind of have some slides that reference what I'm going to do on the Excel file here in just a second. So, whoops. So, I've got this Excel file, which was to population hypothesis test blank. There's a lot of additional information on this file that we're not going to use, right? I think. In fact, like the Midwest and the South here, I have some examples of some stuff from prior to the previous exam where we're looking at kind of just doing one population examples, finding sample proportions, building some confidence intervals for one population examples. We're not kind of dealing with any of that. All I want to show you today is, no, not this. What I want to show you is, here we go, the suicide data sheet. All right. So let me zoom in here a little bit. Okay. Now, I had kind of this for every county, right, in a couple different time periods, what their kind of suicide deaths were for males and females, and then I also kind of did the rates here. Now, I was going to look for kind of the motivating example here was whether or not kind of the genders, like whether or not there's a difference in suicides across these genders. Right? So if I look within each county, it's unlikely that I have kind of these massive, like predominantly male counties. There is some variation, but for the most part, as long as I'm looking within the same county, those differences, right, are kind of in a way controlling for population. It's not always an even 50-50 split, within a county of males and females, but it's pretty close. So that was kind of my motivating example. If we really wanted to do this, we could kind of use the rates, but the numbers get kind of small. It's a little bit easier to think about just the difference in the actual number of deaths here. Okay? So I created this difference variable, which was just within each county, right, in each year and county, take their male suicides and subtract their female suicides. So I'm really calculating my difference variable here. Right? So if I'm thinking about, can I do a hypothesis test with that? I'm going to just test for whether or not we'll do a two-tailed test here to begin with. So I'm just going to think about whether or not my null hypothesis here is going to be, is that true difference, what I want to do, less than or equal to 0? And my alternative is that true difference, is it greater than 0? So I might think that, maybe I've heard somewhere that male suicide rates tend to be quite a bit higher than female, and so I want to test for whether or not this is true. Is that true difference between male and female suicides across these counties, is it positive, right? Or is the male suicides greater than female suicides here? Okay. So what I can do is, once I have this difference variable, it's pretty easy to just find the mean of that variable by using the average function, right? Control shift or command shift on a Mac, hit the down arrow. var.s, find my sample variance for that difference variable. And then my sample size, as we've used before, just use that count function, right? Counts up the number of observations I have here. Right? So this is kind of all this, we've used these quite a bit. Yeah.
Did you say we're doing a 1 or 2 tailed test?
So here, right, for this example, I think the answer key might be something different, but I might kind of go back and forth here for a second. So if I'm doing, is the difference greater than 0, what type of tailed test do I have? One tail or a right-tailed test, right? I can do this for a 2-tailed test, and I probably will. I'll show you what's different, right? So for my test statistic, that's really just a matter of, do I still have it up here? No, not in general form. So let's go back here. It's just a matter of getting, where is it? Yeah, this guy entered in, right? Well, I have my sample difference, the variance on that difference, and my sample size all in Excel. And this assumed true difference, well, I'm just saying, is it greater than 0? So that assumed true difference, I'll use the value of 0. So I'm going to enter that into Excel. So take my sample difference, which was just the mean of that difference variable, subtract that hypothesized true difference, which was 0, but I'm going to still select that because I'll show you what happens if it's not 0. Right? That's why I'm kind of putting this in. Right? If it was 0, I can essentially ignore it, right? Subtracting 0 doesn't change anything. I then take the square root of that variance of the difference variable divided by my sample size, okay? So I get a pretty large test statistic here, right? We'll kind of interpret this here in just a second. But if I want my p-value for a right-tailed test, what I'm thinking about is, for a right-tailed test, whatever sample evidence I find, I want the area in the right tail, and that would represent my p-value for a right-tailed test. Well, I'm using the student t-distribution because I only have a sample variance. So the function that we use in Excel, when we know like this t-value and want to find the area to the left or right of it, is t.dist, right? Now, it would be kind of tough if, I'll show you how to do it one, I'll show you the other way. So I select my test statistic. I then tell it what my degrees of freedom is, which is just my sample size minus 1. And then this third thing, which is cumulative, we said we always put comma 1. That gives us the area to the left. Well, we wanted the area to the right, so what else do I have to do? Yeah, I have to subtract that from 1. So I get a p-value of about 0. Why is it almost 0? Yeah.
Because if you have over 100, then it's basically the same as a standard normal distribution.
So that's true, right? I could actually, if instead of using that t.dist, I use that norm.s.dist, and I selected this and put comma 1. Oh, sorry, what did I forget to do? Subtract it from 1. I'd still get 0 because they're almost indistinguishable. But why is the value actually, for my p-value, so low? Yeah, right? We're 39 like if I'm trying to show this on the board, right? We found sample evidence that's 39 standard deviations above that assumed true value of 0. We'd be somewhere way out here, right? So the area to the right of it is going to be very, very small, or approximately 0, okay? Excuse me. So, that's how we would do kind of this right-tailed test. Now, what would change if instead I wanted to do a 2-tailed test? In fact, the only thing I would change, I'd still have the same test statistic, but instead I would do what? Yeah, once I had the area in that right tail, I'd have to remember I need to multiply it by 2, right? So you kind of think about here, this would be for a 2-tailed test, right? Well, now if it's essentially 0 when I multiply it by 2, I'm still going to get almost 0, right? So it's not that interesting yet. Now I also could have done t.dist. They have kind of this right-tailed test option. which kind of just subtracts it from 1 for you if you wanted to do that. So hopefully if I do this, I still get 0, right? What I'm telling you is true, right? So this just basically subtracts it from 1 for you. Now here, it is 0, but some of the different formats have like functions have different formats built into them. So notice this is formatted as kind of this general. Let's see what this one is. Is this a general one? Yeah, but let's make them both scientific so we can actually, I'm guessing if I change this one to scientific. Surprise it. Why is this a little bit different? Did I select? So it must just keep more decimals with the right-tailed test here. Like some of them just have kind of slightly, different formats built into them, right? We'll see what happens if we change things here. This will be a little more interesting. So let's say that instead of 0, well, I'll show you the shortcut first, and then we'll go back to that. So I can do this process where I find the test statistic, I then find the area to the right of it. If it's a two-tailed test, I can multiply it by 2. But there's this really nice built-in function, which is this t.test, right? So what t.test does is you can select the original data that you want to look at. So before I found this difference variable, right, if I don't want to like muddy up my worksheet by creating this new variable, I could actually have just selected the male suicide variable here, put a comma, right? Go back up there so I can show you. The second thing, well, what's your second array? Well, that was my female suicides. So I'll select the second variable that I was wanting to use, put a comma. Go back up here so I can show you this again. The third thing is, well, what type of tailed test do I have? Let's do the one-tailed test first, right? So do kind of a one-tailed test. Then kind of what's the type here, right? Well, notice it gives me 3 options. The one that we're doing is matched pairs. So that's going to be option 1 there for the 4th thing. So this should, behind the scenes, kind of calculate the difference variable for us. Then behind the scenes, calculate the sample mean, the sample variance, and the sample size. Behind the scenes, calculate your test statistic, find kind of the area that's more extreme than that test statistic. It's one-tailed test, so then it's done, right? So notice we're getting still essentially 0 here, right? If we can format these all the same, they're all showing us 0. Right? Now, if I treated this as a two-tailed test, the only thing I would change there is kind of change this number of tails to 2. Right? And kind of notice that's going to change the size of my p-value because it's going to be multiplied by 2. Yeah?
So the last one's always going to be 1 for the type?
If it's a matched pairs like what we're doing right now, yeah. We can actually use this t-dot test, and I don't think I'm going to have you, I don't have any assignments or anything that you're going to have to use it on, but you actually could use this t-dot test as a shortcut to do 2 population difference and mean examples. Yep. Which is, I think, I'll show you where you could see that if you're interested. Like I said, I'm not going to have you do that on an assignment, but I can show you where an example of that is on this worksheet. So those are kind of all the different things that we could change. We'll see that these kind of hopefully they reproduce similar answers if we change some things here. They're just also close to 0. It won't really matter once we actually get some interesting p-values. So, I was testing for whether or not that true difference is greater than 0 or even in the two-tailed if it's different than 0. Well, I found a mean difference of 44. That's pretty far away from what I assumed to be true. So let's instead assume that maybe it was something much closer to that value. Let's say like 42, right? In which case, if I'm thinking about what my new test statistic is going to be, well, before, right, when I found that this was like the sample difference was 44, and I was assuming the difference was 0, well, that was very unlikely. Well, now I'm going to assume that this difference is 42. So you can think about, now I should kind of be centered around 42 here, right? So now seeing 44 should be much more likely, right? My p-value should increase. I maybe won't be rejecting as easy because, with these p-values of 0, I'm rejecting at any level, right? I mean, it's less than any alpha. So I'm going to change this value of 42. Notice it's still pretty small, right? I guess the formatting here kind of looks janky, so let me show you. I don't know, scientific here. So change it from the scientific formatting. Kind of see here for a one-tailed test, now you can kind of see the format, it doesn't matter. That .RT or subtracting it from 1 yourself give you the same p-value. Now the p-value is a little bit higher, right? It's 0.01008. So here we actually couldn't quite reject at the 99% level. Right? But what couldn't we reject? Well, we couldn't reject that the true difference in suicides is greater than 42 between men and women, right? Well, now notice, what about 40? Well, now 40, the p-value is really, really small again. I actually could, based off my sample evidence, say that per county, the average difference in male and female suicides is 40, right? So if I think about the difference in male-female suicide deaths here, I'm saying that I can reject that it's any value kind of greater than 40 at the county level, which, you know, however many counties there are in the US, that's a huge number of deaths, right? So based off the sample evidence I found, I can reject that the true difference is anything less than 40 or anything lower, which, you know, is pretty crazy, right? I mean, that's a huge, you know, for one county, it's a high number of deaths. But if we think about multiplying that by the number of counties we have, we've maybe just stumbled across something that's pretty relevant to policymakers, right? Now, if I want to do the two-tailed test, right, we said all we have to do is multiply it by 2. So let's go back so we actually have some numbers that are a little bit easier to see here. Okay, so I multiply it by 2, I get my two-tailed test. You know, my p-value would be a little bit higher because now evidence on either side, right? Now I'm just trying to say, is it anything different than 42? But why is my kind of p-value not changed here, right, using that shortcut? Well, the problem is this t.test shortcut, although it's very useful and you know, saves us a lot of time, it's a built-in formula into Excel that can only test against the value of 0. So notice when I change this up here, excuse me, my t.test value wasn't changing. That's because it doesn't have the option to test against any other value than 0, which, like I said, more often than not, we are going to test whether or not that difference is greater than 0, less than 0, anything other than 0. But if we ever have a situation where we want to use any other value, we can't use that shortcut, which is why knowing how to kind of walk through this hypothesis test, like line by line, and what we're actually doing is important, right? A lot of the times we have these black box built-in formulas, but they don't allow us kind of as much flexibility as we would like. Right? And, you know, here, based off the sample, you know, evidence, like, well, yeah, clearly, I mean, even without doing this hypothesis test, I could probably assume I can reject this null hypothesis when I find that the sample difference is 44 per county, you know. But if I wanted to, you know, then narrow it down using that t.test, I can't, right? I can't narrow down like what the true difference might actually be. But if I know how to do all the individual steps and calculate that p-value, well, now I can start to reject, say, even 40 as the true difference, right? So, you know, that's kind of showing you how we might want to, you know, not just use these built-in functions, even though they're a little bit easier, because we can actually say even more powerful things if we understand how to do these intermediate steps. Okay. Any questions on any of that? Do you want to see another cell again, or I'm doing anything here? I know I threw in some different stuff from the complete file. You know, and I left this empty here as well. You know, I could use that if statement again. It's going to be the same thing we were doing before, right? No matter if I, you know, depends on if I want to do the 1 or 2. We'll say we're doing the one-tailed test. If my p-value is less than alpha, comma, I'll put in that word reject, comma, if it's not, I'll put in the word fail, right, for fail to reject. Now, if I'm copying this down, I want to use the same p-value, but I want to test it against different levels. So I'm only going to freeze that p-value reference. Now, when I copy this down, I'll get my rejection decisions. If I do different values, we'll see, okay, sometimes I fail to reject at higher levels, even if I can reject at lower levels. Okay. Any questions on that? It's really what we did with one population stuff, so it's kind of a little bit of a review there, but I did want to show like you could like kind of do this completely. And if you always set it up here, you kind of can remind yourself, I can reject with 90 and 95% confidence, but not with 99. Okay. Any other questions on this? Okay. So it's kind of nice. We can also do this, and I won't walk through this completely. I left it blank here. I guess let me pull up the complete one because we're not going to take time to do it because I know that I'm not going to have you do this on any future assignments, and I want to kind of get us to some interesting like ANOVA and linear regression stuff here. So here's one I have, if you're just interested, Like I said, I'm not going to make you replicate this in any future assignments. But let's say I had two population examples where I have male and female. I think I have male and female BMI, right? And I've got only sample variances. I put in this crazy formula to find our degrees of freedom, right? If you remember, I said I wasn't going to have you guys use that. Well, this is what it would look like if you had to use it, right, in application in Excel. Kind of round it down, round it down to the next nearest integer. Well, we could do confidence intervals. We could do hypothesis testing with it. And it's really just kind of getting those test statistics that we were using on that second exam, using kind of these t dot dis dot 2t or, multiplying by 2. We kind of talked through this with one example. We had an assignment. That was the one that was due Friday for one population. We could do all the same stuff with two populations, right? It's just slightly more complicated, or shouldn't get complicated, longer formulas. But all the same principles would apply in terms of finding the critical values and finding the p-values. But one nice thing that we could do is to avoid all this additional work, right, for both these is, where is it? There it is. I could use this t-dot test. So what I did here was I selected male BMI. Now this one's a little goofy. It says go to the female data worksheet and then select that same column, which was H, which, if I go up here, was female BMI, right? So now that t-dot test will take male BMI and female BMI, treat it as a two-tailed test, right? And then the type, let me see if I can get it to show up here if I delete this. It should tell me what type options I have available to me. Why isn't it doing that? There we go. So I can do a matched pairs, which is the one that I just shown you, or I can do two samples where we have different variances, which is essentially every example we have, right? So I can look up here. Oh yeah, I'm going to have two different samples where the variances are different. And so I'll choose type 3. Now what this is going to do is it's going to go through, find the difference in the sample means, like we had on the problems prior to exam 2. It's going to calculate the test statistic. It's going to find the probability of seeing that test statistic or anything greater. It's a two-tailed test. It'll multiply it by 2 for you. If it's a one-tailed test, it won't, right? And it will return to you the p-value. So it's essentially a shortcut to finding the p-value if you're looking for the difference in means, or a shortcut to find the p-value if you're just looking for the kind of average difference, right? Or these matched pairs examples. And the way that you identified that in the formula was 1 was going to calculate, use those two variables and do this matched pairs for you. And if you put a 3 into that t-dot test, it treated it as though I have two different populations. What's the difference in the means from those populations? But once again, the problem is here, it can only test against that value of 0, right? So even, with this, these types of problems as well, it's important to know how to do the, calculate the test statistic and find the p-value not using that t-dot test, because the only value you can ever kind of use as your assumed true difference is 0. And we know that in application, we might want to use values other than 0. Not, more often than not, we are using 0, but we might want to use other values as well, okay? So like I said, I'm not going to have you kind of replicate any of this on future assignments. This is potentially, we might give you some matched pair stuff, right? So for the sake of what you're doing, that type is always going to be 1 in any assignments that we might have, okay? Any questions on this? So it should be kind of a lot of review. And like I said, to be completely honest, a lot of this is me setting it up so you have a couple easier problems on that final exam to kind of bolster up your grade there, right? So we've got a little bit of time. I'll kind of introduce the next idea. We're going to definitely go over it way more in depth next class. So let's get out of these matched pairs. We did some of that stuff. So here we go. So the next thing that we're going to want to do is, like, we've already seen how we can look at two populations and say, all right, is one of these populations have a higher mean than the other, any mean, different than or less than the other group, right? Well, what if we want to test for differences between more than two groups, right? So maybe I have, people under age 20, people between 20 and 40, people between 40 and 60, and I'm looking at average incomes. And I want to say, does average income vary across these groups, right? Across this age distribution, essentially. So really what we're starting to think about is, I have this variable, right? I just said it was the mean income. And I think that there's this other characteristic, right? However I've grouped these populations, that might influence that variable. So if I look over these different groups' average salaries, do I see that based off of kind of age, I see a difference in the mean salaries of these different age ranges, right, or these different age groups, right? So what we're going to be doing here is more kind of technically called ANOVA, which is stands for analysis of variance, but really, don't let it kind of fool you. We're not looking at the differences in variances. We're really using ANOVA to test for the difference in means across groups. It's just that, this gets kind of complicated. Think about if we had different groups of different sample sizes, when we think about the sample variance for each of those groups, well, depending on the sample size, some of them might be higher or lower, even if they started out with the same variance, right? So we're going to be having all these distributions that don't have the same variance, and we need to take that into account, right? So we use this kind of ANOVA, right? Now, the first thing ANOVA we need is that we're going to have normally distributed populations, right? So this is a little bit of a stretch, but we think that we have an example where the populations will be normally distributed. We can use this ANOVA. Now, when we say the populations here, really if we have large enough sample sizes, or kind of think about our populations of our sample mean distributions, as long as we have high enough sample sizes, they're going to be approximately normally distributed, which is usually how we kind of deal with this first one, right? Or, we also need to have this thing where we assume population standard deviations are equal, right? So this is kind of the initial standpoint of ANOVA. We'll see with two-way ANOVA, we don't really need this anymore, but at least for the first kind of examples we'll look at with just single factor ANOVA, we're assuming the population standard deviations are equal, which isn't that crazy if we're looking at kind of a very similar variable, right? It's assuming that the population standard deviations on income are the same within each age group isn't as wild as, assuming that population standard deviations are the same in incomes across countries or something, right? So we have to kind of be a little bit careful. And I'll talk through these assumptions when we start looking at some examples next class. And then, as always, we kind of need independence from who's in each sample, right? Each observation needs to be independently selected from the others. And then we kind of have these hypothesis tests, which essentially are, look at all these different population means. We're going to assume that for each group, the average income is the same, right? Because what we're really trying to test for is whether or not there's differences in these population means across these different groups, right? So we're going to have kind of these, essentially think about this as like a two-tailed test, where our assumption is we start out, stack the deck against ourselves, all the means are the same, right? Which is obviously probably not very likely. We'll talk about next class how we kind of work through these examples, but this is just kind of general setup of what we're going to be trying to do, right? So we're taking hypothesis testing, just kind of pushing it even further, okay? All right, I should have those second exams graded by Wednesday's class, and we'll talk a little bit more specifically about those, okay? All right, we'll see you guys Wednesday.